Chapter 8 of 20th Century Inventions, A Forecast. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Esther. 20th Century Inventions, A Forecast by George Sutherland. Chapter 8. Mining. Exploratory telegraphy seems likely to claim a position in the 20th century economics of mining, its particular role being to aid in the determination of the strike of mineral-bearing lodes. One main reason for this conclusion consists in the fact that the formations which carry metalliferous ores are nearly always more moist than the surrounding country, and are therefore better conductors of the electrical current. Indeed, there is good ground for the belief that this moistness of the fissures and lodes in which metals chiefly occur has been in part the original cause of the deposition of those metals from their aqueous solutions percolating along the routes in which gravitation carries them. In the volumes of Nature for 1890 and 1891 will be found communications in which the present writer has set forth some of the arguments tending to strengthen the hypothesis that earth currents of electricity exercise an appreciable influence in determining the occurrence of gold and silver, and that they have probably been to some extent instrumental in settling the distribution of other metals. The existence of currents of electricity passing through the earth's crust and on its surface along the lines of least resistance has long been an established fact. Experiments conducted at Harvard, USA, by Professor Trowbridge have proved beyond a doubt that by means of such delicate apparatus as the telephone and microphone it is possible for the observer to state in which direction, from a given point, the best line of conductivity runs. Under certain conditions the return current is so materially facilitated when brought along the line of a watercourse or a moist patch of the earth's crust, that the words heard through a telephone are distinctly more audible than they are at a similar distance when there is no moist return circuit. Deflections of the compass, due to the passing of earth currents along the natural lines of conductivity in the soil or rocks, are so frequently noticed as to be a source of calculation to the scientific surveyor and astronomer. It can thus be shown not only that definite lines of least electrical resistance exist in the earth, but also that natural currents of greater or less strength are almost constantly passing along these lines. Some of the curious and puzzling empirical rules gained from the lifelong experience of miners in regard to the various richness and poorness of mineral lodes, according to the directions in which they strike, whether north, south, east, or west, may very probably be explained, and to some extent justified, by the fuller light which science may throw upon the conditions determining the action of earth currents in producing results similar to those of electro deposition. If, in a given region of a mineral-bearing country, the geological formation is such as to lend itself to the easy conduction of currents in one direction rather than in another, the phenomenon referred to may perhaps be partially explained. But, on the other hand, the origin of the generating force which sets the currents in motion must first be studied before the true conditions determining their direction can be understood. In other words, much that is now obscure, including the true origin of the earth's magnetism, must be to some extent cleared up before the reasons for the seemingly erratic strike of earth currents and of richness in mineral lodes can be fully explained. Practice, however, may here get some distance ahead of science, and may indeed lend some assistance to the latter by providing empirical data upon which it may proceed. When once it is clearly seen that by delicate electrical instruments such as the telephone, the microphone, and the coherer as used in wireless telegraphy, the line of least resistance on any given area of the earth's surface or any given piece of its crust may be determined, the bearing of that fact in showing the best lines of moisture, and therefore the likeliest lines for mineral lodes, will soon be recognized in a very practical manner. No class of men is keener or more enterprising in its applications of the latest practical science to the getting of money than mining speculators. Nor have they at all missed the significance of moist bands occurring in any underground workings as a very favourable augury for the close approach of highly mineralized lodes. If, then, moisture may be favourable, first, to the presence of mineral-bearing country, and secondly, to the conductivity of electrical lines, it is obvious that there is a hopeful field for the exercise of ingenuity in bringing the one into a practical relation to the other. The occult scientific reasons for the connection may not be understood, but it is sufficient for practical purposes to know that, in a certain line from the surface outcropping of a mineral lode, there has been a demonstration of less electrical resistance along that line than is experienced in any other direction. Also to know that such a line of least resistance is proved to have been, in almost innumerable instances, coincident with the best line of mineral-bearing country. The case is similar to that of the rotation of crops in its relation to scientific microbiology. The art of mining may get ahead of the science of physiography in respect of earth currents and lines of least resistance, as showing where the mineral lodes may be expected. Yet there is no doubt whatever that science will not in the one case lag so far behind as it has done in the other. The first notable service rendered by systems of the kind indicated will no doubt be in connection with the rediscovery of very valuable lodes which have been followed up for certain distances and then lost. In an instance of this description, much fruitless exploration drives, winzes, and jump-ups may have been carried out in the surrounding country rock near the place where the lode last cut out. But, in the absence of anything to guide the mine manager and surveyor as to the direction which the search should take, nothing but loss has been involved in the quest. Several properties in the same neighbourhood have, perhaps, been abandoned or suspended in operation owing to very similar causes. The whole group may perhaps have then been bought by an exploration company, whose modus operandi will be as follows. The terminal of the electrical exploration plant is fixed at the end of the lode where it gave out, or else immersed in the water of the shaft which is in connection with the lode system, and another similar terminal is fixed by turns in each shaft of the contiguous group. The electrical resistances offered to the return currents or to the wireless vibrations are then carefully measured, and the direction of the lost lode is taken to be that which shows the least resistance in proportion to the distance traversed. The work of carrying out such an investigation must of necessity be somewhat elaborate, because it may be necessary to connect in turn each shaft as a centre, with every one of the others as subsidiaries. But the guidance afforded, even of a negative character, resulting in the avoidance of useless cutting and blasting through heavy country, will prove invaluable. Many matters will require attention in following out such a line of practical investigation, which are to some extent foreign to the usual work of the mining engineer. For example, the conditions which determine the short-circuiting of an earth current required to be carefully noted, because it would be fallacious to reason that because the line of least resistance lay in a certain direction, therefore an almost continuous lode would be found. Moreover, the electrical method must only be relied upon as a guide when carefully checked by other considerations. Other kinds of moist formations, both metalliferous and non-metalliferous, may influence the lines of least electrical resistance, besides those containing the particular metal which is being sought for. The water difficulty has enforced the abandonment of very many valuable mines in which the positions of the lode are still well known. Sunken riches lying beneath the sea in old Spanish galleons have excited the cupidity and ingenuity of speculators and engineers, but the total amount of wealth thus hidden away from view is a mere insignificant fraction of the value of the rich metalliferous lodes which lie below the water level in flooded mines. The point in depth at which the accumulation of the water renders further following of the lode impracticable may vary in different countries. In China, throughout whole provinces, There is hardly a mine to be found in which the efforts of the miners have not been absolutely paralysed directly the water level was reached. But in western lands, as well as in South Africa and Australia, the immense capacity of the pumps employed for keeping down the water has enabled comparatively wet ground to be worked to a very considerable depth. The limit, nevertheless, has been reached in many rich mining districts. Pumps of the most approved type, and driven by the largest and most economical steam engines, have done their best in the struggle against the difficulty, and yet the water has beaten them. Rich as are the lodes which lie beneath the water, the mining engineer is compelled to confess that the metal value which they contain would not leave, after extraction, a sufficient margin to pay for the enormous cost of draining the shafts. In some instances, indeed, it remains exceedingly doubtful whether pumps of the largest capacity ever attained in any part of the world would cope with the task entailed in draining the abandoned shafts. The underground workings have practically tapped subterranean rivers which, to all intents and purposes, are inexhaustible. Or it may be that the mine has penetrated into some hollow basin of impermeable strata, filled only with porous material, which is kept constantly saturated. To drain such a piece of country would mean practically the emptying of a lake. Subaqueous mining is therefore one of the big problems which the mining engineer of the 20th century must tackle. To a certain extent he will receive guidance in his difficult task from the experiences of those who have virtually taken up submarine mining when in search of treasure lost in sunken ships. The two methods of pumping and of subaqueous mining will in some places be carried out conjointly. In such instances the work assigned to the pumping machinery will be to keep free of water those drives in which good bodies of ore were exposed when last profitable work was being carried on. All below that level will be permitted to fill with water, and the work of boring by means of compressed air, of blasting out the rock, and of filling the trucks will all be performed under the surface. For the shallower depths, large tanks, open at the top, will be constructed and slung upon trucks run on rails along the lowest drives. Practically this arrangement means that an iron shaft, closed at the sides and bottom, and movable on rails laid above the surface, will be employed to keep the water out. Somewhat similar appliances have been found very useful in the operations for laying the foundations of bridges. The details requiring to be worked out for the successful working of subaqueous systems of mining are numerous and important. Chief among these must be the needful provision for enabling the miner to see through strong glass windows near the bottom of the iron shaft, by the aid of electrical lights slung in the water outside, and thus to estimate the correct positions at which to place his drills and his explosives. For this reason the work of the day must be systematically divided, so that at stated intervals the clay and other materials held in suspension by the disturbed water may be allowed to settle and the water be made comparatively clear. Specially constructed strainers for the mechanical filtration of the water near the ore face, and probably also chemical and other precipitates, will be largely resorted to for facilitating this important operation. Beside each window will be provided strong flexible sleeves, terminating in gloves into which the miner can place his hands for the purpose of adjusting the various pieces of machinery required. Beyond this, of course, every possible application of mechanical power operated from above will be resorted to, not only for drilling, but also for gripping and removing the shattered pieces of rock and ore resulting from the blasting operations. From the unwatered drive or tunnel downwards, the method of working, as just described, may be characterized as an underground application of the open cut system. No elaborate honeycombing of the country below the water level will be economically possible, as it is when working in dry rock. But then again, it is becoming plain to many experts in mining that, in working downwards from the surface itself, the future of their industry offers a wide field for the extension of the open cut system. In proportion as power becomes cheaper, the expense attendant upon the removal of clay, sand, and rock, for the purpose of laying bare the cap of a lode at a moderate depth, becomes less formidable when balanced against the economy introduced by methods which admit of the miner working in the open air, although at the bottom of a kind of deep quarry. While the system of close mining will hold its own in a very large number of localities, still there are other places where the increasing cheapness of power for working an open cut, and the coincident increase in the scarcity and cost of timber for supporting the ground, will gradually shift the balance of advantage on to the side of the open method. At the same time, great improvements are now foreshadowed in regard to the modes of working mines by shafts and drives. Some shafts will in future be worked practically as the vertical portions of tramways, having endless wire ropes to convey the trucks direct from the face or the stope to the reduction works, and thus an immense saving will be effected in the cost incidental to mining. From the neighbourhood of the place at which it has been won, the ore will be drawn in trucks attached to the endless wire rope, first along the drive on the horizontal, and then up an incline, increasing in sharpness till the shaft is reached, where the direction of motion becomes vertical. Near the surface again there is an incline, gradually leading to the level of the ground, or rather of the elevated tramway from which the stuff is to be tipped into the mill, or, if it be mullock, on to the waste heap. The return of each truck is effected along the reverse side of the endless wire rope cable. Ventilation is an incidental work of much importance, which it becomes more practicable to carry out in a satisfactory manner when an endless system of truck conveyance has been provided, reaching from the ore face to the mill, and thence back again. The reason is mainly that the same routes which have been prepared for this traffic are available for the supply of air and for the return current which must carry off the accumulated bad gases from the underground workings. Fans operated by the cable at various places along the line of communication keep up a brisk exchange of air, and the coming and going of the trucks themselves help to maintain a good, healthy atmosphere, even in the most remote parts of the mine. In very deep mines, where the heat becomes unbearable after a few minutes unless a strong wind be kept going underground, the forward and backward courses for traffic and ventilation together are especially advantageous. Prices during the 20th century will depend more definitely upon the cost of gold mining than they have ever done at any former time in the world's history. In spite of all the opposition which fanaticism and ignorance could offer to the natural trend of events in the commercial and financial life of the world, the gold standard now rests on an impregnable base, and every year witnesses some new triumph for those who accept it as the foundation of the civilized monetary system. This being the case, it is obvious that the conditions affecting the production of gold must possess a very peculiar interest, even for those who have never lived within hundreds of miles of any gold mine. To all intents and purposes, the habit of every man is to measure daily and even hourly the value of his efforts at producing what the economist calls utilities, against those of the gold miner. If, therefore, the latter successfully calls to his aid mechanical giants who render his work easier, and to enable him to throw into the world's markets a larger proportion of gold for a given amount of effort, the result must be that the price of gold must fall, or, in other words, the prices of general commodities must rise. If, on the other hand, all other industries have been subjected to the like improved conditions of working, the effect must be, to that extent, to balance the rise and keep prices comparatively steady. From this point of view it will be seen that the interests of all those who desire to see a rise in the general prices are to a large extent bound up in the improvement of methods for the extraction of gold. The question of cheap power does not by any means monopolize the data upon which such a problem can be provisionally decided, and yet it may be broadly stated that in the main of the increased output of gold in the future depends upon the more economical production and application of power. Measured against other commodities which also depend mainly upon the same factor, gold will probably remain very steady, while in contrast with those things which require for the production taste and skill rather than mere brute force or mechanical power, gold will fall in value. In other words, the classes of articles and services depending upon the exercise of man's higher faculties of skill, taste, and mental power will rise in price. Getting gold practically means, in modern times, crushing stone. This statement is subject to fewer and fewer exceptions from one decade to another, according as the alluvial deposits in the various gold-producing countries become more or less completely worked out. A partial revival of alluvial mining has been brought about through the application of the giant dredger to cheapening the process of extracting exceedingly small quantities of gold from alluvial drift and dirt. Yet on the whole it will be found that the gold mining industry, almost all the world over, is getting down to the bedrock of ore treatment by crushing and by simple methods of separation. Thus, practically, we may say that the cost of gold is the cost of power in those usually secluded localities where the precious metal is found in quantities sufficient to tempt the investment of capital. From this it may be inferred that the cheap transmission of power by the electric current will effect a more profound revolution in the gold mining industry than in almost any other. The main deterrent to the investing of money in opening up a new gold mine consists in the fact that a very large and certain expense is involved in the conveyance of heavy machinery to the locality, while the results are very largely in the nature of a lottery. When, however, the power is supplied from a central station, and when economical types of crusher are more fully introduced, this deterrent will to a large extent disappear. The cables which radiate from the central electric power house in all directions can be very readily devoted to the furnishing of power to new mines as soon as it is found that the older ones have been proved unprofitable. No one will think of carrying ore to the power when it is far more economical and profitable to carry the power to the ore. In this connection the principle of the division of labour becomes very important. In its bearing upon the mining industry generally, whether in its application to the precious metals or to those which are termed the baser, and even in the work of raising coal and other non-metalliferous minerals, the fact that nearly all mines occur in groups will greatly aid in determining the separation of the work of supplying power as a distinct industry from that of mining. Ore dressing is an art which was in a very rudimentary state at the middle of the 19th century, when the great discoveries of gold, silver, and other metals began to influence the world's markets in so striking a manner. The ancients used the jigger in the form of a wicker basket filled with crushed ore and jerked by hand up and down in water for the purpose of causing the lighter parts to rise to the top, while the more valuable portions made their way to the bottom. In this way the copper mines of Spain were worked in the days of the Roman Empire, and probably the system had existed from time immemorial. 50 or 60 years ago the miner had got so far as to hitch his jigging basket or sieve on to some part of his machinery, generally his pumping engine, and thus to avoid the wearing muscular effort involved in moving it in the water by hand. It was not until the obvious mistake of using a machine which permitted the finest and sometimes the richest part of the ore to escape had been for many years ineffectually admitted, that the vaner, or moving endless band with a stream of water running on it, was invented with the special object of treating the finer stuff. Jiggers and vanners form the staple of the miners' ore dressing machinery at the present day. The efficiency of the latter class of separating machines, working on certain kinds of finely crushed ore, is already so great that it may be said without exaggeration that it could hardly be much improved upon, so far as percentage of extraction is concerned. And yet the waste of power which is involved is something outrageous. For the treatment of a thin layer of slimes, perhaps no thicker than a sixpence, it is necessary to violently agitate, with a reciprocating movement, a large and heavy framework. Sometimes the quantity of stuff put through as the result of 1 horse-power working for an hour is not more than about 100 weight. The consequence is that, in large mines, the nests of vanners comprise scores or even hundreds of machines. When shaking tables are used, without the addition of the endless moving bands, good work can also be done, but the waste of power is still excessive. The vanning spade and shallow washing dish are the prototypes of this kind of ore dressing machinery. Let any one place a line of finely crushed wet ore on a flat spade and draw the latter quickly through still water, at the same time shaking it, and the result, on inspection, if the speed has not been so great as to sweep all the fine grains off the surface, will be that the heavier parts of the ore will be found to have ranged themselves on the side towards which the spade was propelled in its progress through the water. A sheet of glass serves for the purpose of this experiment even better than a metal implement, but the spade is the time-honoured appliance among miners for testing some kinds of finely crushed ore by mechanical separation. It is to be observed that, besides the shaking motion imparted to the apparatus, the only agency in the distribution of the particles is the sidelong movement of the spade relative to the water. But it makes little or no difference whether the water moves sidelong along the spade, or the latter progressing through the liquid. The ore will range itself accurately all the same. Consequently, if a circular tank be used, and if the water be set in rotary motion, the ore on a sheet of glass, held steady, will arrange itself in the same way. If the ore be fed in small streams of water down the inclined surfaces of sloping glass, or other smooth shelves, set close to and parallel with one another near the periphery of such a vessel of moving water, the resultant motions of the heavy and of the light particles respectively, in passing down these shelves, will be found to be so different that the good stuff can be caught by a receptacle placed at one part, while the tailings fall into another receiver which is differently situated at the place where the lighter grains fall. The main essential in this particular application of the art of vanning is simply that the water should move or drift transversely to lines of ore passing, while held in suspension with water, down a smooth sloping surface. In dealing with some very light classes of ore, and especially of such as may naturally crush very fine, that is to say, with the larger proportion of impalpable slimes, there is a decided advantage in causing the water to drift sidelong along the smooth shelf by other means than the motion in a circular tank. Adopting nearly the form of the side delivery manner, in which the moving band is canted to the side, and the stuff runs off sideways, the sloping smooth shelf can be worked for ore separation, with merely the streams of water holding the fine sand in suspension, running down at fixed intervals. A glass covering is placed very close to this surface on which the streams run, and between the two is driven laterally a strong current of wind by means of a blast fan, which causes each stream of water to drift a little sideways, carrying with it the lighter particles, but leaving on its windward side a line of nearly pure ore. These small runlets can be multiplied on a shelf measuring 6 or 8 feet in length, to such an extent that the machine can put through as much ore as a dozen vanners, consuming only a mere fraction of the power necessary to drive one machine of the older type. Cyanide solution instead of water is very advantageously employed for this kind of operation in the case of extracting gold from crushed ore. The method is to pump the liquid from the tanks in which it is stored, and to allow it to flow back by way of the vanning apparatus, thus providing not only for catching the grains of gold by the concentrating machine, but also for the dissolving of the fine impalpable gold dust or natural precipitate by the action of the cyanide of potassium. Upon the use of this latter chemical will be based the main improvements in the gold mining industry during the 20th century, and conversely, the applications of the old system of amalgamating with mercury in order to catch the golden particles will be gradually restricted. Fine concentrators worked with cyanide solution perform three operations at once, namely, first, the catching of the free gold grains; second, the production of a rich concentrate of minerals having gold in association and intended for smelting; and third, the dissolving of the finest particles by the continual action of the chemical. In fact, it is the treatment of complex and very refractory ores generally, whether of the precious or of the baser metals, that the finer applications of the art of the ore dresser will receive their first great impetus. The vanner, as well as the jigger, will become an instrument of precision, and in combination with rushing appliances, operated by cheap power in almost unlimited quantities, it will materially assist in multiplying the world's supply of metals. This again will aid in promoting the further extension of machinery. Gold will be produced in greater abundance for what is called the machinery of commerce, and the base metals, particularly the new alloys of steel and also copper and aluminium, will be more largely produced for engineering and electrical purposes. The importation, particularly to England and Scotland, of large quantities of highly concentrated iron ore will cause one of the first notable developments in the mining and ore treatment of the 20th century so far as the United Kingdom is concerned. The urgent necessity for an extension in the manufacture of Bessemer's steel, and of the new and remarkable alloys, in which very small quantities of other metals are employed in order to impart altogether exceptional qualities to iron, must accentuate the demand for those kinds of ore which lend themselves more readily to the special requirements of the works on hand. Hence the question of the transport of special kinds of iron ore over long distances will have to be faced, as it has been already to a limited degree, and not only in reference to ores containing a low percentage of phosphorus and therefore exceptionally suitable for the Bessemerizing process, but also in regard to ores which are amenable to magnetic separation. Magnetite, indeed, must bulk more largely in the future as a source of iron, particularly because it is susceptible of magnetic separation, a process which as yet is only in its infancy, containing as it does a larger percentage of iron than any other source from which the metal is commercially extracted. Its employment as an ore results in great economy of fuel, as well as a reduction in the proportionate costs of transport. When ores of iron require to be brought from overseas places, it is obvious that those which will concentrate to the purest product possible, and which are in other respects specially applicable to the production of grades of steel of exceptional tensile strength, will have the preference. Magnetic concentration, or the separation of an ore from the waste gangue by the attraction of powerful electromagnets, must therefore occupy a much more prominent place in the metallurgy of the future than it has in that of the past. Not only may ironstone containing magnetite be separated from other material, but several important minerals acquire the property of becoming magnetic when subjected to the operation of roasting, sometimes through a sulphide being converted into a magnetic oxide. By the use of powerful electromagnets, the poles of which are brought to a point or to a nearly sharp knife edge, the intensity of the magnetic field can be so enormously increased that even minerals which are only feebly magnetic can readily be separated by being lifted away from the non-magnetic material. In some systems the crushed ore is simply permitted to fall in a continuous stream through a strong magnetic field, and the magnetic particles are diverted out of the vertical in their descent by the operation of the magnets. Nor is it only those minerals that actually become themselves magnetic on being roasted which can be so differentiated from the material with which they are associated as to be amenable to magnetic separation. Even differences in hygroscopic properties, that is to say, in the degree of avidity with which a mineral takes up moisture from the atmosphere, may be made available for the purpose of effecting a commercially valuable separation. This is especially the case with some complex ores in which one constituent, on being roasted, acquires a much greater hygroscopic power than the others, the grains of the crushed and roasted ore becoming damp and sticky, while those of the other minerals remain comparatively dry. By mixing with an ore of this kind, after it has been allowed to weather for a short time, some finely powdered magnetite, the strongly hygroscopic constituents can be made practically magnetic, because the magnetic impalpable dust adheres to them, while it remains separate from the grains of other minerals. Hardness, as well as magnetic attraction, is a property of ore which has as yet been made available to only a very slight extent as the basis of a system of separation. If a quantity of mixed fragments of glass and plumbago be pounded together in a mortar with only a moderate degree of pressure, so as to avoid, as far as possible, the breaking of the glass, there will soon come a stage at which the softer material can be separated from the harder simply by means of a fine sieve. There are many naturally existing mineral mixtures in the crushing of which a similar result occurs in a very marked degree, and indeed there is none which do not show the peculiarity more or less, because the constituents of an ore are never of exactly the same degree of hardness. When the worthless parts are the softer, and therefore have the greater tendency to slime, the ore is very readily dressed to a high percentage by means of water. But when the reverse is the case, and the valuable constituents, through their softness, get reduced to a fine pulp, long before the other parts, the ordinary operations of the ore dresser become much more difficult to carry out. Most elaborate ore reduction plants are constructed with a view to causing the crushing surfaces, whether of rolls or of jaws, to merely tap each piece of stone so as to break it in bits without creating much dust. This operation is repeated over and over again, but the stuff which is fine enough to go to the concentrator is removed by sieving after each operation of the kind, and the successive rolls or other crushers are set to a finer and finer gauge, so that there is a progressive approach to the conditions of coarse sand, which is that specially desired by the ore dresser. Much of this elaboration will be seen to be needless, and, moreover, better commercial results will be obtained when it is more clearly perceived that the recovery of a valuable ore in the form of a fine slime may be economically effected by the action of grinders especially constructed for the purpose of permitting the hard constituents of the ore to remain in comparatively large grains, while the other and softer minerals are reduced to fine slimes or dust. In other words, a grinding plant purposely designed to carry out its work in exactly the opposite way to that which has been described as the system aimed at in ordinary crushing machinery, has its place in the future of metallurgy. Light mullers are employed to pound or to press together the crushed grains for a given length of time, and then sieving machinery completes the operation by taking out the dust from the more palpable grains. In some cases it will be found that an improvement can be effected by bringing about the separation of a finer grade of dust than could be taken out by any kind of sieve which is commercially practicable on the large scale. This is more particularly the case in regard to sulphide ores containing very friable constituents carrying silver. A fine dry dust separator may then be employed, constructed on the principle of a vibrating sloping shelf which moves rhythmically either in a horizontal circle or with a reciprocal motion, and which at the same time alters its degree of inclination to the horizontal. When the shelf is nearly level, its vibration drives the coarser particles off, but the very finest dust does not leave it until it assumes nearly a vertical position. A large nest of similar shelves, set close to and parallel with one another, can separate out a great quantity of well dried slimes in a very short space of time. End of chapter 8.